Hi everyone, I'm Jack and I'm going to be talking with you about rate laws. If you have had many sleepless nights wondering how rate laws work, well, you've come to the right place. What is a rate law? Rate laws are what chemists use to relate reaction rates to changes in concentration. Okay, so this is what a rate law looks like. In this law, K equals the rate constant, which is dependent on temperature. A and B are reactants, and M is the reactant order for A, and N is the reactant order for B. We'll explain this on the next slide. It is very important to know that rate laws are experimentally determined. That means that they can only be determined based on experimental data. They cannot be predicted. That is a very important thing to understand. Also, liquids, solids, and intermediates are not included in the rate law expression. We'll talk about this last one later in the presentation. Another little thing that you should be mindful of is that the K used in the rate law expression is lowercase, whereas the uppercase K is used in equilibrium expression. So that's confusing, but just make sure you know that the two variables are not the same. The two constants are not the same. Reaction orders. These numbers show how the rate of reaction depends on the concentration of reactant. For a zero-order reaction, the rate is independent of concentration. For a first-order reaction, the rate changes proportionally with the change in concentration. For a second-order reaction, as the concentration increases, the rate will increase by the square of the concentration. Okay, let's start with the basic structure of our rate law. Well, first we should look at the table and look at our prompt. So using a table, determine the rate law of this reaction. That's what it wants us to do. And here's a table of values that it gave us. On your AP Chemistry exam and on similar tests, you will see this type of table. Like I said earlier, rate laws can only be experimentally determined. Okay, so let's start with the basic structure of our rate law. We know that NO2 and CO are our reactants, and they are not liquids or solids, so we can put them in this expression. Now, we need to look at the table and find places where one reactant's concentration stays constant while the others changes. We need to look at how the rate changes when the concentration changes. Look at trials 1 and 2, these two right over here. The concentration of CO stays constant, while the concentration of NO2 doubles. Because of this change, the rate quadruples. This relationship shows us that the reaction order with respect to NO2 is second order. Now, look at trials 2 and 3, right here. As you can see, the concentration of NO2 stays constant while the concentration of CO doubles. However, the rate stays relatively constant. Because of this, the reaction with respect to CO must be zero order. So here's our final rate law. To find the overall reaction order, add the exponents. In this example, this reaction is a second order reaction, since 2 plus 0 is 2. Reaction order graphs. Sometimes we want to know how the concentration of a reactant and time are related. We do this with graphs. Here are some examples on the following slide. Make sure you notice how the absolute value of the slope is equal to the rate constant K. So, when there is a linear relationship for the concentration of A versus time graph, it is zero order. When there is a linear relationship for the natural log of A, of the concentration of A versus time, it is first order. Second order, when there's a linear relationship for the 1 over the concentration of A versus time graph, it is second order. Okay, here are the integrated rate laws. These rate laws describe the concentration versus time graphs that we saw in the previous slides. If you look closely, you'll notice that they are the equations of the concentration versus time graphs, which we just saw. This makes them useful since we can plug in data to solve for these variables. And yes, notice how they're in this form, y equals mx plus b. In these equations, the concentration of A sub t is the concentration of A at any given time. K is equal to the rate constant, and this variable here is equal to the initial concentration of A. Example number 2, rate laws with reaction mechanisms. Determine the rate law. Okay, so right here you have 2 elementary steps, and these steps make up an overall reaction. So this step is fast, it occurs quickly. This second step, however, is slow. It won't occur as fast as this one. So you might be asking yourself, when doing the rate law, which set of reactants do you use? Well, in a multi-step reaction, the slow step determines the rate law. So this step determines the rate law. Okay, so you're probably thinking that this must be our rate law, right? I mean, it's a good guess since you're using the reactants of the slow reaction. However, this is not the correct rate law. This is incorrect because it includes the intermediate oxygen right here, which can't happen. We have to rewrite the rate law to remove this. And again, intermediates are chemical species that are produced in one step and consumed in the next. So they are not products of the overall reaction. They're simply chemicals that are used to get, they're simply atoms that are used to get to other places. Removing intermediates. Steps to remove intermediates. First, identify the slow step. Second, write what the rate law would be, including the intermediate. Third, using the equilibrium relationship in the fast step, rewrite the concentration of the intermediate in terms of the reactants of the overall equation. Okay, that sounds like a mouthful, but it's not that bad. So here's my work. It may seem complicated, but all you're doing is exploiting the equilibrium in the fast reaction to solve for the concentration of O, and then you plug that into the rate law. So I identified my slow reaction. I jotted down what I thought the rate law would be, but then I noticed that it includes this oxygen, which is an intermediate. So therefore, I looked at the fast reaction, and I know that the rate of the forward reaction must be equal to the rate of the reverse reaction when there is equilibrium. So from there, I was able to use algebraic relationships to solve for the concentration of oxygen right here. And then I simply plug that into the rate law that I had at the beginning with the new term that is equivalent to this atom right here, to this reactant right here. Excuse me. So you condense a little bit, and then you get your final answer right here. Don't let that -1 reaction order freak you out. It's not very common, so you don't have to worry about it. Finding units of K. All right, I'm sure you're super excited to finding units. Units are super fun, so let's get into it. So simply substitute pre-existing units where appropriate. So K doesn't have constant units. Its units change based on the rate law. Here's an example. Find units of K for this rate law. To solve this problem, simply let molarity over seconds equal the units of the rate, and let molarity equal the units of the concentration of NO2. So if you jot down that relationship, you'll get something that looks like this. And if you divide both sides by molarity squared, you will get molarity over seconds. The quantity molarity over seconds divided by molarity squared equals the units of K, which simplifies to 1 over molarity times seconds as your units for K. Okay, that's it. Thanks for watching. I really appreciate your time. I hope that was okay. If you have any more questions, please let me know. I'm sure Miss Nielsen could tell you who I am and where I can be contacted at. Please note that all examples and solutions were pulled from this great chemistry book. You may already be using this, and if so, it's got a lot of good content in it. So that's great. Thanks for watching. Stay flamin'.